This video introduces the concept of determinants. So what is a determinant? Now, they are useful for solving linear simultaneous equation and understanding the properties of such systems of equations. But what you should note very carefully here is that determinant is a definition, because it's easy to think, oh, can I prove it, can I derive it? And don't try, just take it for granted. It's a definition, and note it's only defined for square matrices. So what is a determinant in brief? In conceptual terms, a determinant gives an indication of the magnitude of a matrix. Now, you might be saying, what do we mean by magnitude? So we could say, on average, and that's a very loose term, not mathematically precise, what scale of impact does it have on vectors? So when you multiply a vector, how much bigger or smaller does it get? So we've got some examples to demonstrate this. And students will notice that the effective magnification is direction dependent. That's very important. So as you change the direction of the vector, you get a different magnification. Here's a simple example then. You see we've got a matrix over here, 3, 2, 2, 3, and I'm going to multiply it by a vector 1, 1, and the result is 5, 5. So here, multiplying by the matrix has given me a magnification of a factor of 5. Let's try a different direction. Here, I've used the same matrix but multiplied by 1 minus 1, and you notice the result is also 1 minus 1. So here, the scaling on the magnification is only a factor of 1. So you can see the scaling of the vector depends upon the direction. Here's another example then. You'll see I've used the matrix 10, 1, 18, 2. I've multiplied by 1, 1, and I've got 11, 20. So I've scaled by a factor of roughly 16, not exactly. Next, I've multiplied by 0.1 minus 0.9, and notice I've only got 0.10 in the answer, so the scaling is a factor of 0.1. So very different scaling or multiplying factors depending on the direction of the vector. And an interesting observation is that if a matrix has a 0 determinant, then it means at least one direction can be mapped to 0. So that's one insight you can get from a determinant, that if a determinant has a small value, then that means there exists at least one direction which will be scaled by a very small number. So what's the definition of a determinant then? And here we're going to start by just doing 2 by 2 matrices. You can see I've given big matrix A equals AB, CD, and the determinant, and this is a definition, is given by the diagonals, the product of the diagonals minus the product of the off diagonals, so AD minus BC. Now there's a bit of terminology here. You'll notice I've used vertical lines around the A, and that's the notation people use to define determinant. Here's some examples then. So you see A is 3, 2, 2, 3, and I've used my notation here, and that basically says find the determinant of A. So the answer is going to be the diagonals, the product of the diagonals, 3 times 3, minus the product of the off diagonals, 2 times 2. So here it's going to be 9 minus 4, which is just 5. Now let's look at B. Again, you'll see in my notation here the vertical lines to say I want to find the determinant of B. So the product of the diagonals is 10 times 2, minus the product of the odd diagonals, which is 1 times 18, and that's going to give me 20 minus 18, which equals 2. Different example on here to show the effect on the scaling of different vectors. So I've got a matrix D, and I want to find the determinant of the matrix D. So again, as normal, I do the diagonals, minus 1 times 8, minus the product of the off diagonals, 4 times minus 5. So that's going to give me minus 8 plus 20, which equals 12. So the determinant in this case is 12. Now you'll see I've used the same matrix down here, matrix D, and I've multiplied it by 4 and 1. So what's this going to get? If we take the top row, we get minus 1 times 4 plus 4 times 1, which is going to give me 0. If I take the second row, I get minus 5 times 4, which is minus 20, plus 8, so minus 12. So you can see there's a scaling of about a factor of 3, as well as a rotation there. What about if I multiply by minus 4, 1? What do I get now? So minus 1 times minus 4 is plus 4, and 4 times 1 is plus 4, so I'm going to end up with 8. And minus 5 times minus 4 is 20, plus 8 is 28. And you can see in this particular case we get a much bigger magnification. Different example. D now, you can see, is minus a quarter, 1, a half, minus 2.25. So what's the determinant? So I go the product of the diagonals, so that's 0.25 times 2.25. I'd ignore the minuses because they cancel each other. Minus 0.5, that's the product of the off diagonals. Now I've given myself a hard calculation there because that's a quarter times 9 over 4. So I'm going to get 9 over 16 minus 4 over 16, which is 5 over 16. So that's the value of the determinant. Now let's multiply some different directions. So first I multiply 4, 1. So minus a quarter times 4 is 1. Minus 1. Plus 1 times 1. And again, you'll see I end up with 0. And the next one, a half times 4 is 2. Minus 2.25. So I'm going to get minus 0.25. So you can see here, if I choose a direction 4, 1, it's multiplied to a relatively small vector, so the scaling is quite small. Now what if I do the next one? Minus 0.25 times minus 0.5, that's going to be a quarter times a half, which is plus an eighth, plus 1, I'm going to get 9 over 8. And for the next one, 0.5 times minus 0.5, so that's minus a quarter, minus 2 and a quarter, I'm going to get minus 2.5. So that one you can see the scaling is actually reasonably large. And a final example here. So f equals minus 1 minus 3, 4, 12. So what's the determinant? So I get minus 1 times 12 minus 3 times 4, which gives me minus 12 minus 12, which is minus 24. So you can see here the determinant is actually quite large. In terms of magnitude, I know it has a negative number, but that 24 tells you that if you find the right direction, there's going to be some vector which is scaled by a large number. Now, let's multiply then these vectors. So first minus 3, 1. So minus 1 times minus 3 is 3, and 3 times 1 is 3, so we end up with 6. 4 times minus 3 is minus 12, plus 12 times 1 is 0. So the minus 3, 1 direction goes to 6, 0. What about the 1 minus 4? So minus 1 times 1 is minus 1, 3 times minus 4 is minus 12, so I've got minus 13. 4 times 1 is 4, 12 times minus 4 is minus 48, so I get minus 44. So you notice this particular one has been scaled to a relatively large vector. So a question to finish. Find the value of x which makes the determinant 0. Now these questions are relatively straightforward. You just substitute in the definition for determinant. So we'll do that there. So the determinant of this matrix is the product of the diagonals. There we are. 3 minus x times 12 minus x minus the product of the off diagonals, which here is 52. Combine that together and you just end up with a quadratic, x squared minus 15x minus 16. And I can solve that and you'll see that I get x minus 16, x plus 1. Now what you can do is you can try substituting these values in. So for example, if I did x equals 16, what would the matrix become? I get minus 13, 10.4, 5 and minus 4. Now if you do the determinant of that matrix, you will find that it's 0. And similarly, you can plug in x equals minus 1 and you'll get the same result. So in summary, we've defined the determinant for 2 by 2 matrices and shown that the determinant can be 0 even when the matrix has non-zero elements. We've shown that a small determinant indicates the existence of a direction x, so that when you do matrix A times x, you get a small vector, and that's quite insightful and will be useful in the longer term. And we've shown that a zero determinant for x indicates the existence of a direction x such that a times x equals 0.